All right, this is curve fitting via least squares, video 1. I'll probably do 2 of these. 2 videos, I think will probably do the job. So for an intro, consider this. Consider these 3 points. So I'm going to plot them. We don't need a big plot. So 3 points I want to choose are 1, 1, 3, 2, and 4, 5. So it's pretty easy to see these don't form a line. They don't lie on a line. If you find, for example, a line through 2 of them, you'll miss the other one, and you can see it visually. On the other hand, we might argue there are lots of close lines. I'm going to put close in quotes because we don't really have a formal definition of close yet, which is fine. This is partly what we need to do, is work this out. But you know, if you were asked to draw some lines that were close, you might draw this line, you might draw this line, you might even draw a line like this maybe. Right? These are all close. If you're sort of pretty comfortable with a vague definition of the word close. So there's a question though, is there a best one? Now we don't have a definition of best yet, so like we can't really answer the question solidly, but we'll say for some sense of the word best. So what we'll look at next is we'll look at the least squares line. And it may not be clear what this is yet because we have to define it. And so we're going to pose a question. We're going to say, look, I know that these 3 points do not lie on a line, but suppose I pretended they did. Suppose I tried to convince myself they did, right? If they were to, right? If these points did lie on a line, y equals mx plus b, then what would we have? We'd have, so I could plug them all in, right? So I could get 5 equals m times 4. Actually, let me do it from the bottom one up, just like I did in the book. So we're being consistent. So 1 equals m times 1 plus b. I'd have 2 equals m times 3 plus b. We'd have 5 equals m times 4 plus b. Now, this is a system of equations in the sense that we can think of this like 1m plus 1b equals 1, 3m plus 1b equals 2, and 4m plus 1b equals 5. So this corresponds to the following matrix equation. If I drop in the coefficients, put in mb, and get 1, 2, 5. There is no solution, of course, we know this, because there's no line. But we can find a least squares solution. So remember how this works, right? So if we label these matrices, I'm not going to do all the gory calculations here. If this is our A, and this is our B, then the least squares solution says that the solution, which I'm going to call MB with a hat on it to make sure that we don't think that we're finding actual M and B. So remember, this is ATA inverse ATB. So if we calculate this, there's some calculation in here. We get 17/14 and -4/7. That's a 14 in there. Which means we have this line. So we have the line y equals 17/14 x minus 4/7. Right, that's sort of the line that emerges when we find m and b hat, right? They're not the actual M and B, but they're sort of the hat versions. So there's this question now, like, what does this look like? What have we got? So let me clear the screen, and then I'll redraw the points, and I'll draw this line, and then we'll analyze what we've actually got visually, so we know what sense the word best means. So this is what we've got on our picture. So try and make these axes as reasonable as possible, so we believe the picture. We have points at 1, 1. We had a point at 3, 2. We had a point at 4, 5. It's way up here. We had a line that we just figured out. Which forgot the x in there. 17/14 x minus 4/7. So that has a slope of a little bit more than 1 and a y-intercept right about there. So if you plot this, you get about this. This is what we get. This doesn't need to be perfect. So what's special about this? Let's think about what we minimized, right? So we minimized, according to the least squares formula, we minimized the magnitude of ax hat minus b, generically. Now, in this case, right, this is the magnitude of the matrix A, which is 1, 3, 4, 1, 1, 1, times the x that we found, which is 17/14, negative 4/7, minus the y values. So the y values for us were 1, 2, 5. Now, let's look at what this is actually working out to be if we were to actually calculate this. All right, we don't, in general, need to calculate this, but it's worth looking in this case at what this is, right? So when I do the matrix multiplication, we get 17/14 times 1 minus 4/7. We get 17/14 times 3 minus 4/7. And we get 17/14 times 5 minus 4/7. We get minus the 1, 2, 5. Now take a look at what these are. All right, so the right hand side is really easy. These are the y values we wanted. These, because of our equation up here, these are the y values we actually get. These are the y values on the line. Both of these correspond to the x values of 1, 3, and 5. So what we've got is the magnitude of the vector created by taking the differences in the y values. So now, this is a particularly ugly calculation, right? But so this is equal to, let me write this without too many numbers. This is the square root. So when we take a difference of vectors, we take the difference of the entries and we square those and add them together, right? So what I've got here is the square root of the sum of the squares of the differences between the desired y values and the actual y values. Now, just to make things a little tidier, when we're minimizing a square root, we're also minimizing the thing itself, right? The values, of course, are different, but obtaining the minimum square root is the same as obtaining the minimum big value if we're not caring about the value itself, right? So we can also say we're also minimizing. In other words, if I say the number is as small as it can be, then I'm simultaneously saying that the thing itself is as small as it can be. So we're also minimizing the sum of the squares of the differences of y values between desired and obtained. So last thing, let me draw this picture again and show you on this picture what we're actually finding. And what I'm going to do, I'm not going to draw any axes marks, because the axes marks actually make the picture a little more cluttered. So the line that we've got here is about this. This doesn't need to be perfect for demonstration purposes. So here's the deal. Imagine you went through this and you started taking distances, vertical distances. So you took this distance, and you took this distance, and you took this distance, and you took those distances and you square them. So if you add the squares of these distances, because the blue values in here, the y values of the blue dots are the y values that we wanted, right? And the values, let me mark these because they'll help. These values are the y values we got. Right. So the red values, if you like, those are these values right here. The blue values, the blue y values, are these y values. So what we're doing is we're minimizing those. That's what's as small as possible. Right? So this line, actually let's be cautious. This line makes the sum of the squares of those distances minimum. Right. Keep in mind, it doesn't make any particular distance, like it doesn't make all of the distances minimum, right? You could certainly change the line and have one distance be smaller. You could put the line through a point and that distance would be 0. But if you want to make the sum of the squares of those distances minimum, this is the line that will do it. So this is called the least squares line. Right? Now, this will work for lots of other functions other than lines. So let me clear the screen and then I'll just do a couple of examples just so that we can see what's going on. So 3, we'll say fitting other curves. So here's the point, is that this will work for any function. Like in the previous example, we fitted a line. We can fit any function which has the following property. When you plug in the points that you're interested in, you end up with a linear system. So we can fit any function which, when we plug in our points, we get a linear system. So let's take a look at an example. So consider these points. So we'll sort of play a game as if we were doing some analysis, right? And so you encounter these points. -1, 2, 0, 0, 1, 2, and 2, 3. So suppose you plot these because you're sort of interested in analyzing them. And when you plot these, you clearly don't get a line, right? So you don't get anything that even might convince you it is a line. So we've got -1, 2, we've got 0, 0, we've got 1, 2, and then we've got 2, 3. So maybe like an absolute value, or maybe a parabola, etc. There are lots of things that you think might fit it. So then maybe you conjecture. You go, oh, maybe this fits a function that looks like y equals ax squared plus bx plus c. So in a real world situation, you sort of play a guessing game and you try some functions and you see which ones are good, right? So then you say like, okay, well, if it does fit this function, right? If they were on such a function, what would it look like, right? So if so, right, we play the same game. We plug in the y values for y and then write down the x values. So let me do it in the reverse order right now so we're good. So we have a, so I'm going to plug them in order. So I have a times x squared plus b times x plus c equals 2. With a times x squared plus b times x plus c equals 0. A times 1 squared plus b times, oops, this should be a 0 in there. This is a 1. This is a 2. I'm plugging our fourth point. A times 2 squared plus b times 2 plus c equals 3. So this thing corresponds to the system. Write down the coefficients. 1, 0, 1, 4 in that case. Negative 1, 0, 1, 2, 1, 1, 1, 1. We've got A, B, C. We've got 2, 0, 2, 3. So that has no solution. But the least squares solution, if we calculate this, I'm going to skip over all the calculation, is actually pretty nice. It's 0.75, negative 0.25, and 0.75, which gives us a line. That's y equals a x squared plus b x plus c. So if we plot this, again, I'll go back, and I'll do this without too much clutter because we'd like to be able to see what we've got. We've got this point, we've got these 2 points, and we've got this sort of slightly off center point right here. If we plot this line, so this line goes like this approximately. So I have this, the version I have in the book is much prettier, but that's okay. So well, it doesn't need to be perfect. So it is a parabola, of course. And so again, if we play this game where we find these vertical distances, that vertical distance, this vertical distance, this vertical distance, and this vertical distance, is we've minimized the sum of the squares of the distances. So we fit something that's not a line, which is absolutely fine. Right? Now, just as a last example, we can only fit these, right? So there's a big warning here. Any function which, right here. So let me clear the screen and end on an example, and it goes really quickly because it doesn't work, where we can see why it doesn't work. So consider this. So this is sort of a fabricated example, but that's just to make a point. I mean, they're all fabricated examples, but this one, I'm not worried about the points too much. So suppose you make a guess, right? Let's suppose we suspect that it follows a function that looks like this. And we want to know what are A and B. Now again, in this case, don't worry about why we think it follows this. This is sort of the art level of data science. But suppose you think it does, right? So you go, well, if so, if it did, this is what we get, right? You would plug in the x's. You'd have a times negative 1 plus sine of b times negative 1 equals 1. You'd have a times 1 plus sine of b times 1 equals 3. A times 2 plus sine of b times 2 equals 10. And so if you rewrite this, right, this is negative 1a, this is a a, this is a 2a. But if you look at these next terms, these are not linear in the sense that I cannot write this as a matrix times, in this case, AB equals 1, 3, 10. right? You can try it, and it doesn't work because the equations themselves, they're not linear in the variable that we're interested in. In other words, it's not a constant times a and a constant times b. Like, it's not a constant times b. It's a constant times a, that one's okay, but it's not a constant times b, but there's no way to do this. So what that means in this case is that least squares will not work. We need other techniques. So I'm going to stop there. There's a little bit more I want to say about sort of more general curves and surface fitting, and about like making some guesses as to the function that you've got. And so let me do that in a separate video though, because this is enough for one video.